All right, so in this video, I want to go over kind of the basics on what exactly energy is and kind of the ways that we can think about energy as it's involved in different processes and what units we use for energy, all of that business. So just to remind ourselves, right, why we're kind of pivoting into this lane, as we covered in chapter 1, chemistry is not just the study of like matter and the changes that matter goes through, but it's also a study of the energy that's associated with those changes. So, right, we'll kind of look throughout this chapter at how energy is a part of chemical reactions. And if you continue through chemistry, going into, say, like Chem 162, you'll see how energy is also incorporated into other chemical processes. So let's start by like broadly defining energy and going into kind of different classifications of how energy is presented. So first off, energy is defined as the ability to do work. So we'll get into in this chapter like what exactly work is, because it's not like the same as, the kind of work that we're familiar with, doing like a job or doing your homework, those sorts of things, right? There's kind of a more defined thermodynamic definition of work. But, right, our kind of big classifications of energy include kinetic energy, which is the energy that has to do with motion or movement, and potential energy, which has to do with an object's position or what it's made up of, so its composition. And so with these two classifications of energy, right, you can consider an object having a total energy that's just the sum of its kinetic and its potential energies. Now, a classic example to kind of illustrate the difference between kinetic and potential energy, I'll show right here, right? So imagine I have a ball at the top of a cliff. And so this ball, because it's up higher off the ground, has a higher potential energy, right? So again, the potential energy has to do with like where that object is positioned. This ball is up high off the ground, that raises its potential energy. If I were to just push that ball off the edge of the cliff, though, it would begin dropping down, right? And so as it's moving down the cliff, it now has kinetic energy, right? That energy of motion, that energy of movement. And so what the ball is doing there is it's converting the potential energy that it had up above into kinetic energy. As it goes lower and lower and lower, closer towards the ground, right, it's losing that potential energy, but it's just converting that into the movement, into that motion of kinetic energy. So before we move further, let's kind of lay down some ground rules for how energy behaves and how we can think about energy. So the first rule is that energy, when it's being, say, converted from potential to kinetic energy, right, that is a conversion. It's sort of a transfer of energy. The energy itself is not being lost. It's just kind of being moved around in different ways. So this is kind of a similar idea to the law of conservation of mass or the law of conservation of matter, right? Where mass cannot be destroyed, it can also not be made out of thin air, right? Energy is kind of the same way. You can't destroy energy. You can't just like make energy out of nothing, right? But instead, you're kind of transferring or converting that energy by different means. The second thing that I want us to keep in mind is in terms of stability. When something has very, very high energy, it's kind of unstable. And so it would be preferable then to reach a lower energy state, kind of a more relaxed state, as we call it. Right? I think of it the same way as when I'm just lazing around at home, I would prefer to be at a lower energy than maybe something unstable and high energy like that. So right, to kind of illustrate these ideas, I want us to consider this scenario where I have a weight tied to a rope and it's hooked up to kind of a pulley mechanism. And so, right, say if I want to lift the weight up off the ground, I'm going to pull on that rope. That's me using up my energy, right, to lift the weight up. So, right, that's kind of a transfer of energy right there. I'm using my own strength and my own energy to lift the weight. And that then, in turn, is raising the potential energy of that weight, right? When the weight is on the ground, it's at a lower potential energy, but when it's up higher off the ground, it's at a higher potential energy. Now, if I were to then, say, release the rope and release the weight, right, because it's now in this high, unstable position, the weight is naturally going to want to move down to a lower state, a lower potential energy, and so that's why the weight then drops down to the ground. When it does that, right, it's taken that high potential energy, it's converted it into kinetic energy by moving down to the ground until eventually it hits the ground and stops. Right now, it's at a lower potential energy and it's transferred all of that energy that was behind it from when it was moving to the ground surrounding it. Right, so there's always kind of this passing of energy, this transfer of energy in different forms, right, in potential or in kinetic energy. Now, another way that we can think of potential energy is in the form of chemical energy. So, right, previously we've been talking about potential energy basically just as like how high it is up off the ground. That's kind of our Newtonian version of potential energy. But another key part of that definition of potential energy was the composition of an object. So that's really like chemically how much energy is stored in a substance. This energy can be stored in the form of, say, bonds, like little connections between the atoms, also between what are called intermolecular forces that kind of hold the molecules together in a substance. Those are ways that potential energy is a bit more on the atom level, right? More chemically involved. In a way, this definition is still kind of basically based on position, right? So if you think about like, say, a cation and an anion, right? A positive charge and a negative charge. If they're really close together, they have like a strong charge attraction between them. So, right, a strong bond there, and that's very stable then. But if the ions are very far apart from each other, then they don't have as much of that, positive to negative attraction, that force that kind of holds them together. And so that's just based off of, right, the position of those atoms kind of defines then how much stability that compound has. Now, an example of chemical energy being used to then convert into other things, right, would be like you go to fill up your car with gas. And while gasoline itself is not a pure substance, right, there are certain compounds in gasoline that when combusted are going to release energy, which we then use to power like our cars and make those move. Another example of chemical energy that we all do ourselves, right, is like eating food to gain energy from that, right? So when we eat, we're taking the energy that's stored in our food and we're converting that into energy for us. So again, it's kind of that transfer, that movement of energy. And it's important to keep in mind that like everything has some amount of energy associated with it. Mostly we think about kind of the objects that are just sitting in place, having a lot of potential energy, but we'll also see later in this chapter and later even in like the end of the general chemistry series that even solid objects that are just kind of sitting in place, they actually have some kinetic energy associated with them. It's just so small that we like can't really notice it. Now, really the last thing that I want to go over in this video are the different units that we use to present energy. So our most common derived SI unit of energy is called the joule, which is represented with a capital J. 1 joule is equal to 1 kilogram meter squared per second squared. All right, so this conversion is included on our formula sheet, but another common unit that we'll use for energy is called the calorie, or abbreviated here as CAL, right? So again, thinking of like food as a source of energy, right? We will often see the word calorie on nutrition facts and food labels and things like that. And so this is where that unit actually comes from. I do want to make a distinction though, that the calories that we're kind of used to, which I'll call like food calories, those are actually different from the calories in science that we use. I know it's very confusing and annoying. So the distinction between just like a normal calorie and a food calorie in terms of their abbreviations is a normal calorie is a lowercase CAL, a food calorie has a capital C, right? So just note that distinction. Now these different units are all related by the following equalities, right? Where 1 capital C calorie is equal to a kilocalorie, or 1,000 lowercase c calories, which is also equal to 4,184 joules. Now we'll get into actually like using these different units and representing, actual amounts of energy, but one thing that I want to actually like warn us of is that the joule itself is a very, very small unit. It's not going to be uncommon for us to see certain processes as having thousands of kilojoules associated with them, right? So we're going to see some really big numbers when we're thinking about energy, and that's totally normal, right? It's just something to keep in mind. And again, we'll see some more worked out examples in the later lectures. But so, right, this is just kind of an introduction to energy, an introduction to the units that we use for energy. Please let me know if you have any questions, and I'm always happy to help.